Test. Action.
Oh, we're recording now?
Alright, yeah, I forgot to record, although everybody was here first watch, everybody's here.
What?
I'm guessing nobody's gonna go back and watch it tonight, but whatever, maybe. So, yeah, you should. Here's, so again, one more time, I had this up yesterday on the quiz, or tomorrow. We've got, pretty much, I would say, I haven't added up the points completely, but I would say pretty much half from each section, half on limits, half of the points on the slope fields. We're not going to spend hardly any time talking about the differential equations or the slope fields or those kind of things. You just be able to, look back at those worksheets, whatever. Now, I do have a practice problem on Newton's law of cooling that you can work on today. So as far as remember, we said, of course, this would be the part where you would use you will have your calculator, so you want to be able to solve. You'll be able to want to plug that in. Plug in your numbers, your room temperature, your initial conditions, that kind of stuff. Be able to plug that into that and be able to do that with the calculator and solve for those things. Somebody in the other class was asking me. They said, "Well, can I just use my calculator to subtract and then divide by the A and then do the log of both sides, and like you would if you were using a TI-30, let's say?" Well, absolutely. You don't have to use that solve command to solve the equation. You can just use your calculator like you would a TI-30 and just do that. I mean, if you're more comfortable doing that, that's fine. Or you can just use the solve command to solve for the K or the T or whatever it is you're solving for. So anyway, got to do that. Now, I did mention yesterday, probably we'll put this one on the calculator part as well, just to balance out the two sections a little bit, where you've got to sketch in your little slope segments, even though you're not really going to use your calculator much for that, other than you have to calculate some of those slopes or whatever. But just probably throw that on there. And to be honest, that's the way any calculator part of a test is, like on the AP test. It just says in the directions, you may need a calculator for some parts of this test, right? So just because it's on the calculator part doesn't mean, oh, gee, I should be using a calculator, right? It's just a tool that you could use if necessary on that section. So the matching would be no calculator, and the sketching the solution curve. Well, that could actually be in either part, sketching the solution curve. And then, of course, this will all be no calculator here. So just quick review. So this basically sums up what we had in our notes yesterday. If I'm doing a limit as x approaches a number or as x approaches infinity, I got one of three things that's going to happen. I'm either going to plug in and get a number, okay, or high powers dominate. In the case of this one, maybe you do high powers dominate kind of thing or whatever, and you get a number. Or you're going to get 0 over 0, infinity over infinity, or something like this that you can turn into one of those. But if it's one of these two, then you can just use L'Hopital's rule. So you have a lot of those where you can use L'Hopital's rule. Or you could factor and do some of those other algebra techniques we've had in the past too, so don't forget about those. And sometimes with infinity, you can just reason your way through it. Like it says, which is growing the fastest, right? So sometimes we just kind of reason our way through it. Or things where, okay, this is insignificant. This is so small compared to infinity squared. This is just... doesn't matter, and then you can reason your way through it. So don't forget about that. And then the other thing that can happen is you can get a number divided by 0, which we know means vertical asymptote, which is going to involve some infinity scenarios. We say it doesn't exist, but we have to tell why, which usually means left and the right. See what's happening on the left and the right. Or it might be like an x squared is just going up to infinity. The top power is growing way faster than the bottom, so it's just going to infinity. And so the limit does not exist. So those are basically the things that can happen. All right, so which ones you want to look at on the homework?
56 through 80.
Okay, let's narrow it down a little bit. 36.
Ooh.
So 36 is one that had the graph, or did it?
No, it was the
Oh, it's just explained. Okay, so let's talk about that. Explain why L'Hopital's rule can be used to evaluate this, but not this, okay? So if I plug a pi into this, what's sine of pi? 0 over 0. So L'Hopital's rule can be used. Okay, if I plug a pi into this one, what's cosine of pi?
1. Or
That's why. L'Hopital's rule is only used for situations where you get 0 over 0 or infinity over infinity. Right? And so that's a really good problem, just to make us stop and think that sometimes we overuse, we get so infatuated with L'Hopital's rule because we've worked a couple and then do the derivative, and pretty soon that's your first step. That should never be your first step. Your first step is always direct substitution, right? You plug pi in, you see what you get. If you get 0 over 0 or infinity over infinity, then you can use L'Hopital's rule.
Can we do 35?
Yes, please.
Okay? So 35 is referring to this graph right here. So, and I like these ones with the graph, not that you'll have those on there, but you could, right? It really makes you think about the rule, and they're a little bit non-traditional in how you do it. But again, you first start with direct substitution. So you plug in a 1, and you plug in a 1. Okay? So that gives you f of negative 2 over f of 4. So you go up there and you look at negative 2 and you get 0, right? And you go up to the f graph and you look at 4 and you get 3.5. What's 0 divided by 3.5? 0. So one of three things can happen when you do a limit, when you do direct substitution. One of them is you just get a number, and that is your answer. The limit exists and you're done. Okay? So again, sometimes we get confused by those because we're expecting something like L'Hopital's rule. For example, 34. If you plug a 1 in here, you get f of 1 over f of negative 2. Now what's f of 1? 0. What's f of negative 2? 0. Aha. This is the one where we say, we got to keep going. This is indeterminate. We have to keep going. So one of the ways we can keep going is L'Hopital's rule. Right? We had the factoring, we had all that stuff. None of that really works in this scenario. So we can do the derivative of the top, which would be f prime of x, and the derivative of the bottom. What do you do to do the derivative of that? Derivative of the outside, yeah. Leave the inside alone. Multiply by the derivative of the inside. Derivative of the outside is f prime. Leave the inside alone, negative 2x, times the derivative of the inside. So now we plug in our 1. F prime of 1. So that means we go to the graph and do the slope of 1. But I can't scroll up there. But what's it look like? It looks like about 1.5.
Yeah.
Okay, roughly. And then plug a 1 in here, you get f prime at negative 2. So you go over to negative 2 and it's down and it's
Negative. It's about negative 2.
Is it? I thought it was a little steeper than that, but negative 2 maybe. But whatever, if you,
Something like that.
yeah, draw, if you get one like this tomorrow, make sure you sketch your tangent line, show me kind of your triangle, so I can kind of see where your number's coming from. But negative 2, let's call it negative 2, times negative 2, which is 4, so 1.5 over 4, which would be roughly 3/8, I guess. If I don't have a calculator, just double the top bottom. So 3/8, I don't know, the answer book had 0.3125, I'm not sure where they got that, but whatever, that's.
Yeah, that's what I always thought. Like, what the hell?
Well, I mean, just depends what you get for those slopes. I mean, but that's the idea. So the key is that you have that, right? So there'd be some good partial credit if you had written this on your paper, and I could tell. And that's the other thing. I walked around, and some of you for a whole batch of those, all you had were numbers. You just had numbers like 56 through 8. How do you just have number? I mean, like you got to do L'Hopital's rule. You got to do on some of those. You had to do a product rule and derivative. So where was that work at, right? I mean, that work's got to be somewhere. You put it on your paper, right? I mean, I'm not sure how you would just get a number other than just looking at the answer, just writing something down. So make sure you're doing that because there's partial credit. Like so, for example, if you do this right here, right? I mean, that's good stuff. You've done a lot of good stuff there. Now, if you mess up on your slope or something, then, but if you just have a number down and it's not right, I can't give, I mean, you're going to lose it all. All right. So anything else on those?
29, 30, 32. 32 is, does not exist, but I didn't know like how to.
Oh, yeah. Yeah, let's look at that from a graphical perspective. So if I plug a 2 in here, so f of 2 is what, about 1.5. And put a 2 in the bottom, I get 0. So right away we say that does not exist, right? So that's that third scenario. You got a number over 0. So that's a vertical asymptote situation. So what we have is an infinity kind of a scenario. So what we have to do is we have to look on the left of 2 and we have to look on the right of 2. Now yesterday when we were doing that, we put in numbers. We put in like 1.999, right? Well, that's kind of the same thing here, right? So plug in a 1.999. Well, if you plug in 1.999, it's still about 1.5. I mean, remember, we said the top doesn't really matter. So just put 1.5. But what about the bottom? If I put 1.999 in here and square it, it's a little less than 4. So what we end up with is a small negative. So that's 1.5 divided by a really small negative. That's negative infinity. So just write that. Just write that. And then 2 from the right. So 2 from the right is, again, about 1.5. And then a little bigger than 2 squared is a little bigger than 4 minus 4. So that's a real small positive. So that would be positive. So there you go. So you need to have those. That would be the answer I want to see. Right there. Okay? So, yeah, that's a good question. And then same thing's true on the graph. See, at least here you had something to plug into on the bottom. Like number 5? Was 5 it does not exist?
It was -1.
Or 3 was? So 3, on 3,
Yeah, for the last one.
yeah, it's x approaches 2. So if you got f over g, so if you go to 2, you get -1. And if you go to 2 on this one, you get 0. Right? And so you got f over g as x approaches 2. So you get -1 over 0. So that does not exist. So you look on the left of -1, or left of 2. So at the left of 2, you're still getting -1. So that doesn't really matter. But what are you getting here? What are you getting to the left of 2 here? You're getting a small negative, right? If you plug in 1.999 into G, 1.999 is right there. It's just a really small negative. So negative divided by a really small negative is going to be a big positive, right? So that'd be infinity. And then just to the right of 2, you're getting a really small positive. So you'd have -1 over a really small positive. So that'd be negative infinity. So that'd be number 3. That's what the part you'd have on number 3 for your does not exist. Okay. We don't usually get it with the graphs, but it does make you think about it a little different way. But you're going through that same process, same reason. Okay. What else?
23.
23. What's that? Read that one, Cootie.
Limit as x approaches infinity, cosine of tangent x over.
No, it's as x approaches 0.
Cosine of tangent, what?
X over X.
Oh, like that? Okay. So x approaches 0, so tangent of 0 is 0 over 0. Oh, okay, yeah, I remember this one. So we get 0 over 0 on the inside. So we have to fix, so that's where we could use L'Hopital's rule, right? There's no algebra we can do. So now I'm just focused on this part here. So tangent x over x is giving me 0 over 0. So L'Hopital's rule says I can do the derivative of the top, which is
Secant squared.
secant squared over the derivative of the bottom, which is 1. Now I can plug a 0 into that. Now secant squared is the same as 1 over cosine squared. Well, I should say, actually I shouldn't say it that way. Secant squared is this, right? And secant is 1 over cosine, right? And when you square a fraction, that's 1 squared, which is 1 over cosine squared. So essentially secant squared is 1 over cosine squared, right? So this whole thing is just 1 over cosine squared, and remember cosine squared really means this. So now we can plug our 0 in. Cosine of 0 is 1. 1 over 1 is 1. But now remember, that was just this inside part. So what we end up with is now cosine of 1, which who knows what that is? Decimal. So just leave it cosine of 1. Yes?
You can't just leave it 0 over 0 and then cosine of 0.
0 over 0 isn't 0. Right? 0 over 0 is indeterminate. Right? It could be anything. Right? That's why we keep going. Yeah. So yeah, if it would have just been 0 in there, then we could have done just cosine of 0. But 0 over 0 is, we don't know what 0 over 0 is. Right? Indeterminate. Can't be determined. Keep going. Okay? Next.
If you want to,
29 or 30. Was that for those with the graphs or no?
yeah.
No.
No.
These are just basic living computing.
These ones here, okay. So, x goes to infinity, so that's going to get bigger and bigger. This is going to get bigger and bigger, right? So you got 2 choices here. One choice would be L'Hopital's rule, right? Another choice would be just knowing which one goes faster. And you have an exponential, which we said grows a lot faster than a power, right? So the top's going to get way bigger than the bottom, so when that happens in a fraction, where's it go to? But don't forget to say this too.
Oh, see, that's, why doesn't, oh, just because it's not a number.
Because it's not a number. It's right. Your answer to a limit is either a number or does not exist, right? And if it does not exist, we got to tell why. Well, here the why is because it goes to infinity. It doesn't go to a number. Right? Now, L'Hopital's rule would be derivative of the top, derivative of the bottom, which still goes to infinity over infinity. So we do the derivative again. And then we get e to the x over 2. And so now as x gets bigger, this is like infinity over 2, which is infinity. Right? So we get it that way. Okay? And then 30, same reason. Oh, no. Totally different reason. Sorry. And I just made a classic mistake there, right? We we get in a habit of, somebody in the other class did this too. They were thinking high powers. High powers dominate. High powers dominate. Well, that only works when x is going to infinity, right? High powers only dominate when the numbers are really big, right? At 0 or at 1, then the powers really matter. I mean, it's not just high powers dominate. So e to the 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0 over 0. Okay, so we got 0 over 0. So we can do L'Hopital's rule. So that's e to the x minus 1 over 2x. Now we put in our 0. Now the mistake people make is they keep doing L'Hopital's rule. You only do it one at a time. You do L'Hopital's rule and then you check to see what you got. In this case, we put a 0 in. We get e to the 0 is 1. 1 minus 1 is 0. Put a 0. So we do get 0 over 0. So we can do L'Hopital's rule again. The top's e to the x. The bottom is 2. Put in a 0. E to the 0 is
0.
No, is 1, 1 over 2,
1 half.
and that's our answer. 1 half. Okay? So again, Connor, that's a classic example. 0 of 0 is not 0, right?
I got that one right.
Yeah. So why on that one did you, that's my question. Why on that one you get 0, 0, and you need to keep going. On the other one you got 0, 0, you're going to call it 0, right? It's,
Lack of reason.
well, no, I just,
You're wrong.
all right.
The book is wrong.
That's good. These are good problems. A lot of different things pop up. 72.
This is fun.
Spencer, what's happening?
Limit of x approaches pi halves, and then natural log of sine x over x minus pi halves, and then all the whole denominator squared.
Okay. So direct substitution. Now, there's no question that tomorrow I'm going to pick one just like on the homework here. You're going to have to know trig values without a calculator. You're going to have to know derivative rules. You're going to have to know stuff about natural log. For example, you better know 2 natural log values for sure. Oops. I didn't mean to do that, but what are the 2? ln of 1 is 0 and ln of e is 1. You got to know the 2. You just got to know. And then the first one, I mean, you should know the log graph too. And of course, that first one you get from here. It crosses at 1. So ln of 1 is 0. So you just need to know that, right? And then knowing this graph, the log graph, that tells you can't have any negatives inputs. It tells you that between 0 and 1, you get negative outputs. It gives you negative infinity. I mean, it just gives you a lot of information. You got to know this in natural log graph. You got to know these values. Okay, you got to know your trig values. I mean, those things are all going to come into play for sure. And I'm going to pick problems where you specifically have to know those things. Now, those would be some easy ones too, right? But, I mean, those should be easy as well. So anyway, we put in pi halves. You got to know sine of pi halves. Sine of pi halves is not 0. Sine of pi halves is 1. Okay, on the unit circle, right, sine is the y. Pi halves is right there. Sine of pi halves is 1. What's ln of 1? 0. Pi halves minus pi halves, 0. Okay, so we get 0, 0. We can use L'Hopital's rule. Now, we can use other stuff, but there's no other stuff that works. Factoring, none of that stuff we learned before works, right? The L'Hopital's rule does. So now we do the derivative of the time. But you got to know your derivative rule. ln of u, the derivative is 1 over u, 1 over sine, times the derivative of the inside, which is cosine. The bottom, we bring the 2 down in front. X minus pi halves to the first times the derivative inside, which is 1. Now in this case, it might actually be helpful, to distribute that. Usually I wouldn't. Well, I'm not going to yet. Okay, so what do? We've done L'Hopital's rule. What's the next step? Put in the pi over halves, see where we're at. So 1 over sine of pi halves, we said sine of pi halves was 1. So 1 over 1 is 1. Cosine of pi halves, that's the x coordinate of pi halves, which is 0. So 1 times 0 is 0. Down here, pi halves minus pi halves is 0. So we still have 0, 0. So now we got to do another L'Hopital's rule. Now, so then you got to think about how you want to do that. So you got cosine over sine on top. And then you got, and here's where I would distribute that now, 2x minus pi on the bottom. So you got to do the derivative at the top. So we got cosine over sine. So if you wanted, you could do a quotient rule there, but that's messy. There'd be a better way. What's cosine over sine? Cosine over sine is cotangent.
That's the one, think so.
Okay? So now what you have is this, right? Now this is still 0, 0 because I haven't done anything. I've just done that. This would be my preference. Now, if you don't know the derivative of cotangent, you don't know your derivative rules well enough. That was one of those that had a star by it. Let's review those real quick. So, of course, we should know sine and cosine. Tangent of x is secant squared.
Cotangent is negative cosecant squared.
Cotangent, and those of you that passed the gateway a while ago maybe haven't been looking at these, but you should if you don't know them. That is, now they're connected, right? And to be honest, I didn't really talk about this at the time, but all of the co-functions are that way. In other words, they're connected. Sine is cosine derivative. Cosine is negative sine. Tangent is secant squared. The co-function of that, cotangent, is negative cosecant squared. Now, what are co-functions? Co-functions come from the word complementary. That's why cosine is called what it is. That's why cotangent is called what it is, and cosecant is called what it is. They're co-functions, which comes from complementary, because they have equal values for their complementary angles. In other words, a sine of 30 is the same as the cosine of 60, right? Degrees. That's where that comes from, those complementary angles, okay? And they're connected with their derivatives, too. What's the derivative of secant?
Secant times tangent squared.
Secant, no square, just secant times tangent. What's cosecant?
Negative cosecant.
Negative cosecant times cotangent, okay? So there's a connection. All the co-functions are negative. Cosecant, cotangent, cosine, they're all negative. And the other ones, sine, secant, and tangent are not. But those, you need those rules. Now, they don't show up very often. That's why I put stars by those in the derivative rules. Those are the ones you probably have to look at every once in a while just to memorize them because you don't run into them a lot. But anyway, back to this. So the derivative of cotangent is negative cosecant squared, and then the derivative, that's just 2. Now, like we just did a minute ago with secant squared and being the reciprocal, what's cosecant squared equal to? 1 over sine squared, and the 2 would stay down here. And again, it's really cosecant's reciprocal is sine, but since it's squared, we just square a fraction, square the top, square the bottom. So it ends up being this. And remember, sine squared is the same as sine x all squared. So now we put our pi halves in. Sine of pi halves we said was 1. 1 squared is 1. So we get negative 1/2 right there. Right? But we've got to know trig values. We've got to know some log values. We've got to know our derivative rule. Con.
Why couldn't you just put the sine x on the bottom?
Where?
There.
Here?
Yeah.
Okay? Not a bad idea. Okay? I like that, as a matter of fact. So right up here, or right here. Let me do that in red. An equivalent, now you got to really be careful, because I've seen what you guys can do, and math students in general, when they start flipping things around from the bottom to the top and so forth, right? But because if we group this as one thing, and we got this times this, like if I have 3 times 2/5, right, I can just make that 3 times 2, I could put that 5 under everything. Now, not if that was a plus, I couldn't do that, but when it's times, I can do that, right? Same thing when I have a fraction up in here. I could actually write that as cosine x, and then my bottom could have been sine x times the 2x minus pi, like that, is what you're saying. Yes, I could have written it that way, absolutely. Now, when I put in my cosine of pi halves, that is 0. And when I do sine of pi halves, that's 1. Put pi halves in here, I get 0. So I still get 0, 0. And so now when I do the derivative, let me do it in red. So the derivative at the top be negative sine. What do you got to do on the bottom? You got to do a product. Okay, you got to do a product. So the derivative of sine. So yes, so there's nothing wrong with doing that. But you got to do the derivative right. Right? I mean, you got to do the derivative right. So derivative of sine is cosine times the 2x minus pi left alone plus sine left alone times the derivative of 2x minus pi, which is 2. Okay, now we put our pi halves in. Sine of pi halves we said was 1. So that's negative 1 on top. Cosine of pi halves we said was 0, which wipes that out. Sine of pi halves we said was 1. 1 times 2 is 2. And negative 1. So that's maybe better. Maybe that's better because then you didn't have to remember cotangent derivative, right? So that wasn't bad. Okay, but you had to do a product, right? You got to do the derivative correctly, obviously, for that. Which is why we did a gateway test and why we have to know derivative, right? I mean, if you're doing a chapter on using derivative, probably need to know how to do derivatives. Okay, another one. Let's keep going. Good practice.
68.
68.
Yeah.
What is it?
Yeah. Limit as x approaches infinity, x squared e to the negative x squared over 2.
So like that.
Yeah, this was.
So as x goes to infinity, this x squared is getting bigger, and e to a negative infinity, what's that go towards? That's getting smaller. That's 0. Okay, so this is that one that we have to manipulate, but it's pretty easy to manipulate because you got negative power. So right away, that would think I would hope you would think of just moving that to the bottom. So this just becomes this, right? So the top's getting big, the bottom's getting big. Okay, but at this point, I don't think you need to do any more.
Because we know the e to the x is getting bigger.
The bottom's going to get way bigger because it's an exponential compared to a power. So the bottom's going to get way bigger than the top. So this is just going to go to 0.
Alright.
Okay?
Now do number
But-
56.
But you didn't think of that. You said, I want to do L'Hopital's rule, right? You got this. Now here's, I want to do this because I'm hoping all of you are sitting there thinking, I would not do L'Hopital's rule. I would just go 0 because I know the exponential is going faster. But something happens here that you may need to know in other problems, okay? So when I do, so let's say you said, okay, infinity over infinity. Hey, I can do L'Hopital's rule. Do the derivative at the top or the bottom. Now, e to the u, remember, is e to the u times u prime, which would be
2x.
just be x, right? 2 times a half would be 1x, okay? Right? Negative, what's negative? No, because I put it at the bottom. Okay, so derivative top. So now, now we got to check it, remember? So x goes to infinity, that's infinity, and this is still infinity. So I could do L'Hopital's rule again. Now the problem is, what do you notice on the bottom?
There's an X on both
Oh.
of them.
Well, okay, yes. But let's say I didn't see that. That's the key. You'd be looking at a product rule on the bottom, which is fine. Sometimes you have to, right? It's okay. But what about the x's? Some of you said it. You can cancel those x's. Now keep this in mind. Keep this in mind because I have seen problems, and I don't know, it may be one of them in here, but I've seen problems where you do the quotient rule, and remember when you, or not the quotient rule, sorry, L'Hopital's rule, do L'Hopital's rule, and what happens is you kick out, so you kick out an x or whatever, and so you've multiplied. Now when you do the derivative again, it's going to mean you're going to need a product rule. And it can get really messy. Now you eventually probably get there, but you a lot of times can save yourself a lot of headaches and a lot of work if you notice that along the way, when you get to that next step, check and see just for a second if you can't simplify it or do something. And in this one, you'd be way better off if you notice that those cancel. Because now you don't have infinity over infinity anymore. You have 2 over infinity, which is 0. So then you save yourself a whole step and not have to do product rule again and so forth and so on. So just keep that in the back of your mind that after you do L'Hopital's rule, you have to plug in and check again, but also check what you ended up with. Maybe it simplifies.
Is there any time where like e to the x power number to the x power, is that other than another number to the x power, is that ever like the smaller of the two? Or, no?
Not when x is going to infinity.
Okay.
All right.
I got, on Simply Simple, that does not exist, but then I forgot how to do it. And I don't even know if that's right.
I got
Okay, what is it? X goes to
Zero
from
from the right.
the right.
Sine of x, ln of sine of x.
Sine of x what?
Times ln of sine of x.
Okay, so first thing we do is we plug in. So sine of 0 is 0. Ln, or sine of 0 is 0. Ln of 0 doesn't exist, but this is where you have to think of the graph. And of course, anytime you see that 0 from the right, there's the reason they gave it, probably a reason they gave it from the right, because something else is going on there. Now, the other time you'd see that's maybe on a piecewise function or something when you had 2 different graphs hitting at 0, and so you want to look at this one versus this one. But we haven't been doing a lot of piecewise. We're mostly these functions. So it's usually a domain issue, which of course you have with natural log. So what this means is when x approaches 0 from the right, we got to think about the sine graph. When x approaches 0 from the right, so if you got a car coming in here, what do you get?
0.
Well, that's where it eventually would hit, but what are you getting as it approaches?
Positive numbers.
Positive, really small positives, right? So when you plug in 0 from the right, okay, you're getting really small positives here. So this is where you have to change how you're doing your substitution just a little bit. So we're getting really small positives. So when you go to ln and put in really small positives, what do you get?
Really big.
Really big negatives. So that's how you come up with the fact that this is negative infinity, right? You don't need a calculator for it. You just need to know what the sine graph looks like and what the cosine graph, or the ln graph looks like. And so that's how you know you're getting negative infinity, okay? Because sine at 0 is approaching 0, but it's really small positives, and then you're putting those into ln, you're getting really big negatives, negative infinity. So we need to do some sort of reciprocal, kind of flip this around.
Flip side.
So you can flip sine. So you got ln of sine x, and then down here, 1 over sine x, right? I can't just move sine x down
I thought,
there. I can't just move sine down there, right? I mean, it's like,
well, explain that a little.
well, okay, if I got 2 times 6, that's 12, right? If I just move the 2 down there, now I got 3. I totally changed the problem. You got to get the same thing, right? We did this back here. We had x squared. We had e to the negative 1/2 x squared. We didn't just move e to the negative 1/2 x squared down here. We did the reciprocal, which was we did a positive, right? You can't just move it down. So what I could do here is I could move down to 1/2, right? 6 divided by 1/2 is 12. See what I mean? So yeah, so I can move the reciprocal down to the bottom. That's what I'm going to do. Okay, so I'm going to do that. Now what do I get? I get negative infinity up here. And what do I get here? I get 1 over 0, which is infinity, right? 1 over a really small number. 1 over a really small number is a really big number. So now I have infinity over infinity. Okay, so now I can do L'Hopital's rule. Now this I would probably write, so this 1 over sine, I would write sine of to the negative 1. Or I could write it as, what's a reciprocal sign? What's a reciprocal sign? Cosecant. Now, I usually try to avoid that if I can, to be honest with you. Because if I avoid cosecant, then I got to remember the derivative of cosecant first of all, and then I got to plug in the cosecants and stuff, and then I end up turning it back to reciprocals anyway. So I probably would just leave it like this. Okay, so derivative of the top. What's the derivative of the top?
1 over sine x.
1 over sine x
Times cosine.
times cosine x. That's the bottom. or the top, excuse me. And what would be the derivative of this? -1, sign left alone, to the -2, times the derivative of the inside, which is cosine. Now, again, somebody else, let me change colors here. Somebody else called the bottom cosecant, which is 1 over sine, right? Let's see. Derivative of cosecant is negative cosecant times cotangent. But now when it comes time to plug into that, you're going to prefer to have sines and cosines anyway, right? Well, what do you have here? This is -1 over sine, and then times cosine over sine, right? Well, look what you're going to get. You're going to get negative cosine over sine squared. Well, isn't that what we have right here in the red? So either way, it's going to end up being the same, whether you call 1 over sine cosecant or whether you call it this. Okay, so let me come back to this one. Let me just write this so I get negative cosine over sine squared. Okay, so let me clean it up a little bit. So I got cosine x over sine, and here I got negative cosine over sine squared. That's kind of, I tried to clean it up and that ran into that. Well, now I got all kinds of algebra I can do to that, right? I can flip this up here and have sine squared x over, and there's a negative there, right? So I can flip this up and multiply. So what happens? Cosine cancels, one sine cancels, and I got a negative in there, negative sine. Come back to this, plug in a 0.
What if we didn't flip it at the beginning?
What's that?
What if we didn't know to flip it at the beginning?
What if you were right here and didn't know to simplify that?
No, clear at the beginning, when you just.
That was
sign
sine.
Yeah, that.
And then you don't.
I had no idea we were supposed to do that. I just kind of kept going with the derivative.
Well, you can't go with the derivative because you can only do L'Hopital's rule if you have 0 over 0 or infinity over infinity. It's the only time you can use L'Hopital's rule. Okay? So, yeah, I don't know how to answer that question. I mean, it's kind of like, you know, we're doing a quiz on quadratic formula and you say, what do you do if I don't know the quadratic formula? Well, you know what I mean? You're in trouble. I mean, that's kind of an extreme example, but the bottom line is, when we went back to, well, I have to pull up yesterday's notes, but when we go back to here, these two, you can use L'Hopital's rule. When you have this, remember the discussion. I mean, when you say you don't know, what you really mean is you don't remember, okay? When we said you have 0 times infinity, remember, 0 is the reciprocal of infinity, and infinity is the reciprocal of 0. So you can always turn 0 into 1 over infinity, which gives you infinity over infinity. Or you can turn infinity into 1 over 0, which gives you 0 over 0. So anytime you have a 0 times infinity, you've got to do the reciprocal thing so you can make it look like what you need for L'Hopital. Okay? Not saying it's easy, but that's what it would look like. And I'm glad we were able to discuss this because I didn't anticipate that confusion of that thing, right? Of how you, when I say reciprocal, right? I mean, what's that rule going back to when you learned division? Multiplying is the same as dividing by the reciprocal, right? Multiplying, or I guess it was the other way around. Dividing is the same as multiplying by the reciprocal. So multiplying by sine x is the same as dividing by 1 over sine x, right? Isn't that the old rule? It's the same thing we did right here. It's just the opposite, right? So dividing by this is the same as multiplying by this reciprocal. Multiplying by this is the same as dividing by its reciprocal. Yeah.
And then if we go over 80.
That's a good one. I didn't know if anybody was going to ask him that. What was it, Matthias? X?
X approaches pi over 2. And then it's parentheses pi over 2 minus x parentheses tangent x.
Okay, so same scenario here about knowing some trig stuff. So if you plug in a pi over 2, clearly the first part is 0, but then the question is what's tangent of pi over 2? And so, one good thing to know is that tangent looks like this, and so at pi over 2, it's going to infinity, right? Now, depending which side of pi over 2 you're on, but basically it doesn't matter, we got infinity, so we got this same scenario. Now, if I was doing this problem, I would change tangent to sine over cosine. I mean, my first strategy with trig functions usually is turn them into sines and cosines because I'd rather work with those. Now, sometimes that makes it worse, but usually it doesn't. So that would be my first instinct. The other reason I would do that is because I know L'Hopital's rule, like our discussion we just had, needs to be a fraction. It needs to be 0 over 0, infinity over infinity. So that will give me a fraction. So I would change this into pi halves minus x times sine all over cosine. And remember, the reason I can do all over cosine is if I have 3 times 2/5, that's the same as 3 times 2 over 5, the whole thing over 5, because this is basically 3 over 1. So it's kind of like thinking this is over 1 and think of that as sine over cosine. So I can turn it into this. Now when I put a pi halves in, I get 0, sine of pi halves is 1, so that's 0. And cosine of pi halves is also 0. So changing that tangent into sine over cosine is nice. But what does that cause to happen now? I do a product rule on the top, right? Do a product rule, but that's okay. I mean, we got to be able to do a product rule.
Could you do the pi halves minus x divided by cosine over sine?
Yes. So could you do? Let me think about that a minute. So we just said you could. This is sine over cosine. So you could divide by the reciprocal, which is this, right? Which then becomes 0 up here, and you put a pi halves in here, you get 0 over 1, which is 0, so it's 0, 0. Now, how would you do your derivative here? Would you do this, or would you change that to cotangent? You would do this derivative, you do a quotient rule? Okay. Go ahead, I'm not going to. But you can, sure you can. Now, see, I don't think that's all bad, but I would call this cotangent, right? Now, what's the derivative at the top? So this helps me avoid the product rule, which I'll finish here in a second. But the derivative here is -1, and what's the derivative of cotangent?
Cosecant squared.
Negative cosecant squared. Now that cancels that, and what's 1 over cosecant squared? That's actually the same as sine squared, okay, because cosecant's reciprocal sine. And so now I plug in a pi halves, sine of pi halves is 1, 1 squared is 1. So I actually like that, although I don't like your idea of doing the quotient rule, but it would work. It would work, it would just be messier. And then if I finish this product rule one, let's do that, because to be honest, if you're going to change things in sines and cosines, sometimes that does make a little more work for you, because you end up with that. But product rule, derivative of the first be -1, sine left alone. I guess I didn't mind product rule here because it's not a very hard product rule. The first one left alone times derivative of cosine, or derivative of sine is cosine, and then do the derivative of the bottom is, no, you're thinking quotient rule, you're thinking quotient rule. We're doing the derivative of the top, and then we're doing the derivative of the bottom. Okay? All right, now we plug in our pi halves. Sine of pi halves is 1, so we get -1. Put a pi halves in here, we get 0, so we get -1 on top. Sine of pi halves is 1, -1. Simplifies it. So either way is fine. Okay? So, I mean, we've spent some time on some difficult ones, but, I mean, they're only difficult because we had trouble knowing our trig rules, or we had trouble knowing our derivative rules. I mean, they weren't, you know what I mean? I mean, which is okay. I mean, that's what's going to make them harder. There'll be some of that on there. There'll be some that'll be easier, too, like some of those earlier ones. But you got to be able to do the whole thing, right?
You still haven't given us our Christmas present.
Or what?
Our Christmas present. So if you wanted to, you could just not